the talk.
Thank you so much, Jens. And well, I really like the title of this talk because in Plone community, we always say that context is the king. So we are going to try to do a talk about natural language, magic, in artificial intelligence on the kings, on the context. So first of all, who we are. Oh, what's about the talk, sorry. First, we are going to start the first step to talk about why we want to talk about artificial intelligence or NLP, natural language processing, on CMSs and what's the useful use case for CMSs. And then Aleix is going to do a talk about what's machine learning from newbies, from start, from scratch, just to learn all the basics about what we are going to talk. Later, we're going to talk about what are the state-of-the-art techniques on natural language processing. And finally, we're going to do a short coding example of how we can use that on JavaScript on the front end. So I think that I may have a skip. Yeah. Who we are, Aleix Ruiz is the guy that it's also on the call. He's going to introduce later. PhD in mathematics, and he works as a freelancer on data science. I'm Ramon, CTO and co-founder of GetFlaps, and Guillotina Framework team member. So, why we think that artificial intelligence is something useful for content management systems? And we kind of focus on these 5 different subjects. A semantic search, in order to search not because we have a keyword that we are looking for, because of the content, the meaning of the content, tagging and classifying content, summarization, translation, and finally extracting entities and the relation between the entities. So just to introduce a bit all these kind of subjects, first, what's semantic search? All we are used about on BM25, TF, IDF, what Elasticsearch, Solr, even the Zope text indexer provides as a BM25 indexing, which provides a kind of a heuristic way of finding a keyword inside a big amount of text. It looks for how frequent is the keyword on the document and does some kind of operations in order to provide the proper document that fits our query. It's really focused to the keywords that we are looking for. Then there is the n-gram search, where we are splitting all these words, these big words, onto smaller ones that we are kind of slicing them, so we are able to find them when we look for parts of the word. Then, of course, there is the fuzzy search that looks for kind of heuristically the distance between one sentence to the other by replacing some letters on the word. And finally, and the reason of this semantic search, what we call the vector search. What's the vector search? It means that you have a sentence that you want to look for. I prefer to drink wine, but you are writing that as I'm ingesting alcohol, or I'm writing that in Spanish, for example, me gusta el vino. So any of the first 2 sentences doesn't have the words that we have on the second. So either BM25, n-gram, or fuzzy search is going to be able to find this sentence when we are looking for the first one. What vectors does is it translates the initial sentences and the destination sentences onto vectors that represents the meaning of these sentences, the semantic meaning. And then we are able to look for the sentences by the distance between the vectors. Classifying and tag content. This is the easier example. Even in 2015, I did a talk in EuroPython that I already was introducing how to do that in Plone 5, a really long time ago, 5 years ago. That at the end is that you have a bunch of documents that have a subject, for example, like in Plone, another bunch of documents has another subject, and then you introduce a new one, and you want to define which is the tag of this new document based on the ones that we already had. Another example of artificial intelligence on CMS is you want to do the summarization. We all know this description field that we have on Plone, that it's going to be try to be a summary. So what if instead of needing to write a summary or a description of your document, it provides an automatic description of what you have in your content. So there is two kind of summarizations algorithms right now. One that it extracts the most important sentences on the text, and the ones that writes down a real summary of the text by understanding what the text is about. The second one is the most difficult one, as you can imagine. Translation. What's translation at the end? What we see in Google Translate, for example, in one language, voy a ir a comprar, it's in Catalan, you translate this sentence into a vector. This vector represents the meaning of this sentence, which if we can have a decode to move again this vector onto text, we can decode that meaning onto different languages, and we can translate the meaning of the sentence by moving from text to vectors and vectors to text. Entities extraction and knowledge graph, that means the relation, it's something that it's really, really powerful, because when you're writing your content, maybe you want to extract your name at the entities. We all know how to extract the cities or the locations or even the names, but imagine that you can define your own kind of entities, and you can train a model that it's able to detect that, for example, you want to look for dates, or you want to look for countries that you're from. So then you can extract all this information and train models to represent the relation between these entities. So these are our most important and most useful and CMS use cases for artificial intelligence that we are using right now. So now, in order to introduce machine learning, I give the word to Aleix, who can continue with a one-on-one on machine learning.
Hi, everyone. I'm Aleix. Thanks, Ramon. The idea for this section is to get the basics of machine learning. So if you know nothing about machine learning, the idea is that you have a general idea of what's going on and what are the main points. If you know machine learning, some of these things will sound familiar to you. So if you have to think in just one idea what machine learning is, probably the most simple way of thinking about it, it's an automatic labeler. An automatic labeler, it's something that you give objects and it gives you a label, and it does it automatically. For instance, if you want if you go to a parking and you see the cards of the car that has a number, you want a program that extracts this information automatically. So the idea is you want to build this automatic labeler. The main thing is how you are going to build it. And the main point in machine learning, it's sorry, can you move back? It's from labeled examples. It's from examples. So you're learning from examples. It's like if you show a child, this is a 0 and this is a 1 and this is a 2, the child somehow manages to understand that there's a 0, 1. And so when this kid sees a new number, a new digit, she's able to say, this is a 1 or this is a 2. So what you have to your starting point is this set of labeled examples. In a very simplistic way, a machine learning model takes as input a database which is from labeled examples, and has a process, an algorithm, or whatever you can think of, and builds a new predictive model, which is a function. It's just a function that when it takes an object, it gives you the label. Since we are going to talk about text, the first worry about dealing text is how can we transform this text in something that the computer is able to compute. There will be lots of matrices and numbers, so you need to transform this text into numbers. The easiest way to do that, it's what's called one-hot encoding, which is basically having a vocabulary that of your text and putting each word for a different position. For instance, in this sentence, for you and for me, the 4 would be the array 1, 0, 0, 0, because it's the first position. The U will be the 0, 1, 0, 0, and so on. And you can see that the second 4, it's again a 1, 0, 0, 0. Okay, so in this way, you can transform words to vectors. The problem is that all the vectors have the same distance. So there is the same distance, or it's as much similar, the 4 and the U, and the 4 and the and the 4 and the me. And this is a kind of a problem because in text, the you and me has a more closer meaning than 4 and. So you can, but for starters, you can use this one-hot encoding at a word level. There is also the possibility of adding all the frequencies, how many times each word has appeared, and you have this thing called the bag of words, which is counting each word how many times appears. And in this case, you would have the 2, 1, 1, 1, which is the 4 word appear twice and the rest appear 1. So in this way, you can transform either words or sentences into vectors. Now let's think of an example. Imagine that you have emails and you want to classify them into being spam or not being spam. For this, the label it's a spam or not, it's not spam. And as we said before, we can transform all these texts or these emails into vectors. If we make a plot of what could possibly be, this is a plot in 2 dimensions, but the vectors, as you saw, can grow as much as the vocabulary. You can have a situation like the image on your left, that you can see that each dot represents a document or a sentence, if you want. And each dot, it's already labeled as either spam or not spam. So if you want to build an automatic labeler, you want to set a region where you will say, if a new email falls into this region, it would be spam. If it falls on the other, it would be non-spam. Again, the most simple way to do it, it's using a line. And this is called a linear model. And this linear model is separating the 2 regions between spam and non-spam. And as you can see, there is some error because there was one black inside the other region. So it's pretty simplistic, but it's the first, the most simple model, and it's very widely used. This model has a technical problem, which is that if a document falls very near the boundary or the line and it moves a little, it just goes from 1 to 0 or to spam and not spam. This change is very, very abrupt on the border. And for technical reasons that we will talk, but just very few later, this is a problem. This behavior is what you see on your right. It's the step function. It goes from non-spam to spam. And what you would have, it's a smooth transition. A smooth transition means that instead of talking about this is spam or this is not spam, you say this is 90% with probability 90% this is spam, and with 10% it's not spam. You would like some kind of degree of being in each label. And that's why you introduced this well, many years ago, there was this sigmoid functions, or you will see there are many of this type, which does this job of transforming something which is very abrupt into something which is smooth. And these type of functions are called activation functions. In this way, you can, next one. In this way, you can build the most simple neural network, which is called the Perceptron. Perceptron was discovered or introduced, I think, in the 50s or 60s or something like that. It's pretty old. And the idea is you build a linear model, and on top of that, you put a sigmoid function. Okay, this is the most simple one. I've been talking about this line, but the problem is, how do you find this line? Because there are an infinity possible lines. This line, it's characterized by some weights, the coefficients of each variable, and finding this line is the same as finding these weights. So the question here in the image, the weights are the W's. The first question is, how do you find these weights? And we will not enter into this, well, Ramon a little bit more later, but this is obtained through a mathematical optimization problem. And the idea is find these weights such that make the classifications the best. So it makes the most margin, if you want, between the two classes, or it does the minimum amount of error, or this kind of notions. And Ramon will announce some libraries, but there are like TensorFlow or PyTorch, which are very well-known libraries where what they do is precisely that. Now, if you kind of understood a perceptron, you can make it much more complex. How? Combining lots of perceptrons. If you had one, now you can have many. And a way to organize this, it's the which is called the feed-forward neural network, which is putting layers, and in each layer you have different nodes. And each node represents one perceptron, so you will have some weight regarding the inputs and activation functions and so on. And in this way, you can build these neural networks that they have tons of different configurations. We can see in the following slide. These are some examples, but there are lots and lots, and every day there appear more, because some of them work better for the problems, and some of them were not so good. In particular, the next one, the next type of a general type of neural networks is what they are called the recurrent neural networks. Recurrent neural networks mean that they process the inputs sequentially. So they have something which is ordered. You have a first object, a second object, a third object, and you process the first one, and the process of this first one goes to the second one, and the second one takes the second object and the process from the first one, and keeps doing this recurrency of processing the new object and the object before. And as you can see on the image, this is perfect for dealing with text, because text has an order, and as humans we read from left to right. So this works pretty well for text. One simple application that you can think of with this type of processing is which is called next word prediction, or the autocomplete. If you use, for instance, Google, well, you do use Google, but in some processors, they suggest you the next word, and a way to doing this, it's training a recurrent neural network that reads the sentence and tries to predict which is the next word. And this is basically an autocomplete. One of the most well-known recurrent neural networks are the so-called LSTMs, which it stands for long short-term memory. And they are recurrent neural networks, as I said. So each model takes an input. In this image, you see that the input is a vector. This can be either words with this one-hot encoding. This can be sentences, for instance, or whatever thing that goes sequentially. And inside each one of this module, it's what you see on your right, which is the LSTM properly. And what it does inside, it does a bunch of matrix operations, because you have vectors as inputs and you have the weights that you have to multiply. So there are lots of matrix operations. There are activation functions, as you can see, the sigmoid and the hyperbolic tangent, and they combine the result, the outcomes of these multiplications, or they multiply them, and they do this kind of things. And these, I think that the first one was from the 1997 or something like that, and they become pretty well known, and somehow they are a little bit used nowadays. In particular, you can use this kind of architecture to do what Ramon said at the beginning about named entity recognition. What is named entity recognition? It's you have a sentence and you want to distinguish some of the words of the sentence, because you want to give a tag for each one of them. For instance, in this sentence, UN official EQs heads for Baghdad. You want to understand that UN is an organization, EQs it's a person, and Baghdad it's a location. And you can also do, for instance, detecting dates or other stuff of things. So far, we've been talking about these architectures and how to do encodings, and there's one thing that Ramon also said at the beginning, that it's the embeddings. The embeddings is this idea that you can take a sentence or a word or a whole document and transform it into a vector. And the way of doing this, and this vector should retain some semantic information about what you are trying to encode. So, for instance, two sentences that are similar should have vectors that are one near the other. And this was a pretty good discovery that I don't remember the dates, but maybe in 2014 or something like that. There was the first one, which is called Word2Vec, that they did these embeddings from the words, and they discovered there was this semantic meaning of the sentences. So how can we get these embeddings? Imagine that you already trained a neural network, for instance, for predicting the next word or for classifying documents or whatever. This network will look something like this one that we are seeing. Probably maybe more complex, but the idea still works. The last layer of the neural network has as many nodes as labels you want to have. For instance, if you train a neural network that classifies digits, the last layer will have 10 nodes because you have 10 digits. If you want to train a neural network that predicts the next word, the last layer will have as many nodes as your vocabulary have. In the name entity recognition that we saw before, if you want to have as labels the person, location, organization, and date, you will have 4 nodes as outputs. So this layer, it's pretty particular for the program that you're working, but the layer before is the result of processing all the sentence or all the documents and building a vector that can be as large as you want, because the length of that vector you can choose. So usually when you have trained a very interesting neural network, what you do is you remove the last layer and you keep the previous one, because the previous one, it's giving you a vector that encodes all the sentences or all the words, or depending how you do that. As an example, you can see this work. You have you have link, but it's one out of many because there are many type of works with embeddings. These guys, what did is make embeddings of books, which is kind of difficult because encoding the whole information of a whole book, it's difficult, but they did this neural network and they embed, for each book, they had a very long vector in a way that similar books have close positions on as vectors, and you can see that the green ones are non-fiction and they are all together. There are the blue ones which are science fiction, which are also all together. And again, this is a representation to dimensions, but the vectors are pretty large. So one application of this type of thing is what Ramon said, which is semantic search, because once you have this vector, you can search for the nearest vectors, and you are searching for documents that have a similar meaning. Okay, so I think that's all for my part. You're muted, Ramon.
Yeah, thank you so much, Aleix. It's really interesting always to refresh all these concepts when you ask to focus on these techniques. So now we're going to go just to show which is the state of the art on this natural language processing. What we've been explaining with Aleix, it's kind of what's been valid until maybe 2 years ago, where it's still used a lot, but something happened that changed most of the paradigm on our system. So which are the tasks that these new technologies are going to help? So mostly for conversational kind of behaviors, filling masks, it means you have a sentence, you have a piece of text and you want to fill the slots, question and answering, summarization of text, classification of text, and generating new text. Imagine that you want to create documents or maybe generate answers for a conversation, and translation, as I said. So we are kind of getting a bigger spectrum of solutions. So what changed then kind of the paradigm was in 2017. It was an article that it was attention is all you need. No? And what they started to think about is based on the LSTMs and the recurrent neural networks, that LSTMs, for example, goes in one direction. Then they started to do bidirectional LSTMs. So we go in one direction and the other direction in order to keep also the end of the sentence in favor on the context. They're kind of taking each of the words and analyzing which is the effect of that word for the rest of the words in each of the sentences on a really dense matrix. So attention on the element to understand what affects it. In this case, for example, the animal didn't cross the street because it was too tired. Understanding that it means the dog, it's something that you need to focus on each word and understanding the context around it and see how it affects with thousands of millions of sentences that may kind of do the same kind of effect and relation. There is another example of checking which is the focus on the sentence in order to understand how it affects the rest of the sentence at the moment of computing the embeddings. This technique allowed also to go forward and create these kind of vectors that were able to transform from one text that it's being computed with this attention to a vector, and then doing decoders to transform to original text. And this was called transformers. Transformers, it's mostly kind of a technique that you're using a decoder and encoder that are different embeddings, transformer matrix that at the end you're multiplying matrix vectors and all these kind of structures in order to get other vectors, and then you get back to identifications, IDs, tokens that you can get back to words. So This is a long sentence. I should not write long sentences on talks, but I really like it, and it's really interesting. So understanding the advantages of what's a recurrent neural network, a convolutional neural network. We didn't talk about that, but convolutionals are what's mostly used by visual machine learning, self-driving cars to any of the visual robotics kind of appliance. Understanding using the two kind of architectures and moving with the lucky GPUs and all the power of computational that we have, we were able to compute these really complex matrices that analyzes the from one word to the rest of the sentence or the rest of the context, which is the value of that word. There was also AlphaStar that it's also from DeepMind, from Google, that they created a transformer to analyze the behavior of a game called StarCraft in order with LSTMs in this case, in order to determine which is the behaviors of the enemies on the game. So it has a lot of other appliance or other use cases, and this is one that I like because I like StarCraft, so that's great. So after this attention, finally, what came into the game was BERT, one of the bidirectional encoding recurrent transformer. That it's a model that was open sourced by Google. There's a lot of hundreds of thousands of hours doing computation with different tasks. So focusing on detecting which is the next sentence, filling gaps on sentences, on doing, I think that 4 or 5 different tasks at the same time with the attention and bidirectional encoding algorithm from bidirectional LSTMs. We were able to have a model that was able to encode a sentence in a semantic vector that was able to give us a position with 712 dimensions, any sentence or any word. So this was so costly computational that they gave to the community, and it's open. You can download the weights of the matrix. I think it took, it may took 4 full days of TPUs. With GPUs will be really much more expensive. There is a lot of parameters on this metrics, on this embedding, 345 millions. Amazing. Was kind of breaking all the state of the art of natural languages, and everybody started to move to these kind of technologies. But then Wild West came, and all the different companies were trying to open their new models that were kind of with more parameters and more parameters and more parameters. So they started to do Big BERT, and they started to do more and more and more and more. And for example, right now, a GPT-3 has, I think that nearly 180 billion parameters, that it's really too big to fit in any computer. T5, that it's one of the Google one, has 11,000 million parameters. And each one is kind of more data, crawling all the web, all the text from all the web, and analyzing with hundreds of TPUs with a lot of hours. Well, all these embeddings are really amazing. So we can get even closer and better vectors. But with the BERT baseline model, we can really get amazing results. And we can run that on our laptops, even on Raspberry Pis, even on mobile phone, and we will see later that on our browsers. So which are the frameworks that are mostly encouraging these technologies? PyTorch, TensorFlow as the computing engines, and Hugging Face has transforms and tokenizer as a way of generalizing the different kind of algorithms in a simple library. They did an amazing effort on this site, and it's so great to play around all these different architectures. So all these things are amazing, and BERT is amazing, but what's mostly amazing is that you can take any of these architectures that have already been compiled for hundreds of days, and it's already a really interesting result. And you can take the last layers of these embeddings or these models, and you can train with your own data. So you can have your own domain-specific model more accurate to your specific domain data. So some examples about these libraries, for example, you can easily use transformers, and you can just call, you want the pipeline of summarization using the T5, that it's one of the latest. And you can just say, summarize this sentence in a sentence with this size. Or you can create your own custom model, defining that you want an NER model, and load a basic one, remove some layers, and train with your own data with really a short amount of time. So there is also, if you want, some services that provide you this as a service. Flaps, for example, my newest startup, provides you can push data, train, predict, and uses Plone REST API in order to interact with the API. Hugging Face has prediction API, and IBM Watson has also training and prediction. Google and all the other main partners also have some APIs to push data, train these models with embeddings, and get your models so you can use your inference, your prediction. So finally, and I really have not a lot of minutes left, I'm going to go to a small example of how we can use these technologies in JavaScript, in the browser itself. So all the examples that you can find on the internet, mostly if you look for it about TensorFlow.js, that it's the library that we're going to use, are about visualization models that you can do with your webcam, some kind of games like moving your lips and detecting if you are looking at the camera or wherever. But there has been some kind of enhancements on the JavaScript machine learning wall that helps, for example, to have LSTMs or recurrent neural networks, embeddings, and even there is a small version of mobile BERT that you can use in the browser. It really consumes half of the process of your browser, but you can really run it. What we're going to see here is a simple use example that provides us with a really shorter embedding that really provides you with vectors. Just why we should use them in JavaScript if you have servers that run that. One of the most important things is the privacy. No, you are not sending anything to any server to compute anything. You can run on your browser, and you can have a really fast answer. And it also uses the GPU from and the WebGL accelerator from the browser in order to run it. So this example is going to be, we need some ingredients, we need some data, and we need an architecture. The data that I'm going to use is the data from toxicity on Commons, that it's a published data set with Creative Commons that you can download and use it. So the code of what I'm going to show you now, it's on this repo, in my GitHub repo, PC 2020 King's Magic. And just to go showing a bit, there are some Python notebooks that you can, for example, in this case, we are loading a model from TensorFlow Hub. That this model, it's one that is called Universal Sentence Encoder. That it's a simple embedding. That it's really small, fits on the browser, but it's only only in English. So you cannot use translation in this case. After we load this model, we can run it and transform all the sentences that we're going to use onto IDs and predict which is the vector. For example, in this case, I'm using a word, a sentence, and a full paragraph, and then I'm having 4 different sentences. In this case, at the moment that we are processing these sentences to convert them to vectors, for example, here we have the vectors of these words, elephant, or I like to go climbing, I prefer mountain. These are the vectors that we get from each for embedding all these sentences. If we check the cosine distance of these vectors, for example, we can see that the distance between sentence 3 and 4, so I like to go climbing and I prefer mountains, it's closer, it's only 0.39 than I like to go running. We go to run every morning. And it's even farther than how old are you? we can see here that the distance with how old are you, it's 0.8. So this gives us a proper distance with semantic meaning of all these sentences. Then there is a convert notebook that converts the data that we saw on toxic, a training that trains a model that helps to design if a sentence is toxic or not. You can check here, this is the data set that you get where it says for each sentence if it's toxic or not. And finally, there is an index HTML that loads the sentence embodiment, transforms the sentence into a vector, and predicts with the model that we train if it's toxic or not. And we can see it running here. So for example, I can write some example sentences that, for example, I say, I love Plone community. And now it's not toxic, good. But if I say, use my framework, I will kill you. It's toxic. It's able to define properly which are the toxicity of a word. For example, this sentence, you deserve to not be alive. Something that if you take each word, it's not toxic by itself, but the meaning of all of them, it checks that it's toxic. There is still some need fine-tuning on this algorithm, on this model, because for example, you can say, you should use multi-adapters, and this should be toxic, and it's not toxic. So that's all, and thank you so much for listening. I hope that we ended on time.
Yeah, thank you very much for this interesting talk. I learned a lot. So next is we have the one question, it's a Slido, but I don't know exactly which. Yeah, I read the question. The question from Asko was, are these methods language independent or do they need to be adapted for each language?
That's a really good question. So for example, there is, it depends on which is the data set that it's being trained. BERT, for example, has one of the models that they published. It's the main one is in English, of course, but then there is one that is multilingual BERT that has 111 languages on the training data. So you are able to get embeddings for any of these 111 languages, and you get a similar embedding in different languages. Then there is some kind of other BERT, including BERT models that are published that are Chinese or some other more complex languages. Then, of course, from the any of the other models that there are out of Roberta, all the different flavors, there are some that are multi-language, some that are only in one language. There are people that it's in Finland. For example, there is somebody who did a BERT in Finland language that you can use, that it's only able to do embeddings.
Okay, great. There's another question from Adrian. What is the framework? Could you introduce more in the slide?
The framework, it's called, so there is PyTorch. PyTorch is like it's done by Facebook, and it's like a computational machine that builds a graph that to do complex operations with metrics. TensorFlow is the same with the Google flavor. It has some good things like TensorFlow Hub, where you have a lot of models that are open to download and use. And then there is one framework that it's mostly used for transformers, for this kind of techniques, that it's called transformers. So it's quite easy, and it's on Hugging Face page. And I think that I wrote it here. I have the URL here down on this slide. It's called huggingface.co/models, where there is all the models that everybody open sourcing or publishes their models. There is a Spanish one, Italian. There is mostly all the languages. You can play with that and publish your own models there.
Great. So then no more questions. we have the face-to-face after the talk now. You find